Hello everyone. Today I'm pleased to share a significant result of his cost-counting area of research. The paper globally consistent normal orientation for point cloud by regularizing the winding number field solves a long-standing problem, which is the reconditioning of a point cloud with the imperfect role-playing cloud data under imperfect conditions. First, let me start with a brief introduction to the point cloud data. Point cloud is a dataset of series points resulting from 3D scan. It's not widely used in modeling related fields. The point cloud, each point represents a part of the object. Due to the limitation of scanning, we cannot get the whole of the plane. So we need to estimate the normal based on the existing point cloud to get the relationship between the point and then get the whole plane. Currently, this research is challenging. Previous optimization-based algorithm and machine learning-based algorithm can only solve part of this problem. It is still difficult to deal with noisy, sparse data and point cloud with complex topologies. This article will mainly focusing on those problems. To solve the problem of estimate the global normal direction, there are two things need to be solved. The first is how to determine a point is outside of the surface or inside of the surface. The second is how to connect the point on the surface into a plane. This article introduced two mathematical aspects, the winding number and the Voronoi diagram. Winding number is a method of distinguish whenever a point is inside or outside of the closed circle surface. Based on this method, you can determine a point in a point cloud is inside or outside of the object. If the point is outside of the object, the winding number will be 0. If the point is inside of the object, the winding number will be 1, larger than 1. So another concept, Voronoi diagram, which is a mathematical structure that it will be used to partition a space based on the nearest neighborhood principle by several generating points. In other way, the whole space can be divided into several subspaces by some point. This is a good way of estimate normal vector of a point cloud because it gives a plan to calculate normal vector. In its implementation section, this paper introduced an optimizer called LBFGF and 3 optimized directions. The first one, 0, 1 term, used to force winding number converge to 0 or 1. The main reason of setting winding number to binary value is to given a uniform normal direction. The second one is balance term. This term will encourage the 0 and 1 winding number to be evenly distributed. The article there assuming that the internal and the external point in the point cloud are evenly the same. So this term is used to reduce the effect of the noise in the normal vector estimation. The last one is alignment term. The alignment term is used to align the normal vector to the point of the Voronoi diagram, which ensures the consistent of global normal estimate of normal directions. Therefore, the full process will be first, randomly assign inner and outer point of the point cloud and generate initial normal vector based on the Voronoi diagram, and iterate using LEFGS optimizer to obtain a global normal directions. Next, the article compared their work with the procedures, and the results clearly show that their work has a better performance on the noise, sparse data, and the data cloud with complex topology. The most striking thing of this is their performance for the sparse data and complex topologies. Due to the excellent performance of Voronoi diagram on the service estimation, together with the critical role of the winding number, it's possible to draw a better result of sparse data, and also will be effect on the complex topology structure. However, this method still have some drawbacks. First is the consistency between the service and the interior of assumption. Will force some non-closed service into a closed one due to this assumption. The second problem came from the Voronoi diagram. On the one hand, the excellent performance of Voronoi diagram can let the global normal direction slowly converge, but the Voronoi itself is highly related by the generating point, meaning that it is weakly noise resistant. Even though using some robust method like winding number, the system can still fail in extreme cases. For example, some point cloud with extremely low signal to noise ratio. Moreover, for unevenly distributed or extremely sparse point cloud, the normal direction will become too converged under the consistent of the Voronoi diagram, and as a result, the local structure and feature will be lost. In general, this is a very informative article, and this introduction of the concept of spatial construction in topology to normal estimator is a good idea. I think adding some other algorithms such as k-means clustering or meshing might be the good way to solve the global normal direction estimation.